Hello, my name is Alexey Potapov, and the paper I am presenting is entitled Univalent Foundations of AGI Are Not All You Need. First of all, let me explain motivation behind this subject. Foundations of mathematics played a huge role in the emergence of the field of artificial intelligence. The notion of algorithms was formalized in the course of an attempt to overcome the foundational crisis in mathematics, which was one of the main steps towards invention of computers. Physical charge unit physics basically implies that our brain is a computer, while the physical symbol system hypothesis says this explicitly. Already, traditional set theoretic and logical foundations of mathematics gave rise to Prolog and whole good old-fashioned AI approach. Although it was criticized and abandoned to a certain extent, deep neural networks are built using mathematics with the very same foundations. While development of cognitive architectures in AGI frequently turns into studying computational formalisms and design of programming languages. Thus, contemporary work in AGI still boils down to mathematics and its foundations. At the same time, there are novel candidates to foundations of mathematics, and the question naturally arises if these novel foundations can play the same role for AGI, which classical foundations played for good old-fashioned AI. There are two major candidates, category theory and homotopy type theory, which both have already played a considerable role in design of modern programming languages. There are works of applying them, especially category theory, to different questions in AGI, but can then become the entire basis of AGI. We consider this question with respect to homotopy type theory, which constructiveness means that it is amenable to a direct computational implementation. For us, it's not an abstract question since we are developing a novel version of cognitive architecture. Let us first start with reviewing dependent types as a possible way to represent knowledge and reasoning. Main components of dependent type languages are variables, types, and type constructors. In the simplest case, type constructors just enumerate objects of a certain type. For example, if we want to represent Socrates and Plato as objects of type human, we can introduce them as constructors of this type. It should be noted that type assignment are judgments. That is, they cannot be negated or refuted or appear in other propositions. These are types which represent both mere propositions and sets, as well as can be higher and types which enable uniform knowledge representation about entities and statements about them. Let us immediately note that constructible means existent. That is, if there is a type constructor, it makes something unconditionally existent for our knowledge system. Types and their constructors can be parameterized. Together with standard operations on types such as dependent sums and products. This leads to a powerful way to model natural language as outlined by Corfield in the book Model Homotopy Type Theory. Consider the simplest example. Here we have human as a dependent type. So we can form propositions whether some entity is human or not. Mortal is also a dependent type, and its constructor indicates that all humans are mortal. We can then form a proposition as mortal Socrates type and prove it by showing its inhabitants. Complex and rich expressions can be formed about entities, their relations, proofs over propositions themselves, etc. There is some discussion on how better to represent knowledge on natural language statements using type systems. One can also wonder how to construct proofs instead of just verifying them by type checking. However, we are interested in more basic stuff, and this example is enough for us. In particular, if we are interested if homotopy and dependent type series as a sufficient and suitable basis for cognitive architectures. In this context, one question arises where types and type constructors come from. In mathematics, we can construct any system of types or axioms and prove theorems in them. The question is in applicability to the real world. And when we are talking about AGI, we face the same question. Imagine that we don't have all humans are mortal as a judgment. Rather, we have facts about concrete persons. Then we can prove that all humans are mortal, but constructing a total function of a corresponding type. In this case, the syllogism will render to be uninteresting. We either need already to know about mortality of every person, and there will be no sense in proving that something is immortal due to being a human, or we will not be able to provide total F. Nothing really new here. It's an old problem of deduction versus induction. The issue, however, is that we want to describe induction mathematically in a constructive way and implement it programmatically. And thus, we should be able to do this in a language of type theories. Imagine that we've created a machine learning system expressed in terms of types, their constructors, etc. It can be sound and so on. We can prove theorems about it, but won't the question of its applicability to the real world arises once again. How this question can be answered? The answer, which should hopefully be obvious, is empirically. There are numerous aspects to this answer, and it should be not understood simplistically. We can go a level deeper and consider the agent at the moment of time separately, as it is done in Alexey. Consider Solomonov induction for simplicity. It's not constructive, but there are computable versions, say with Levin search. In order to implement a form of Solomonov induction in type-theoretic language, we still need to introduce some types. We can consider them as some pure mathematical constructions, but we will still want to assign them some real-world interpretation and apply them to the real data. Basically, this means that this is a model in a scientific sense, and the question of its adequacy to reality can still be posed. Solomonov induction has nice properties as a model, imposing almost no limitations on data distribution, having guarantees of convergence to true predictions. One may agree that this sounds good enough to turn applicability of Solomonov induction to input data into a built-in judgment rather than consider it as a proposition to be proven. But it doesn't really work in practice this way. Why? Obviously, it doesn't account for computational complexity. There are some models that do account, but they are still models which appear to be not too adequate to reality in one way or another. Of course, it doesn't mean that they cannot be improved and suddenly become a basis for real AGI. But my point is that we cannot prove purely mathematically that some model will work as a real AGI. This poses an interesting question. Is the Gödel machine can formally prove that non-trivial rewrites, non-homotopical, violating some sort of self-equality rewrites will be beneficial? For example, it could never accept a simpleton gambit unless its acceptability is built in axioms. Avoiding the simpleton gambit, that is, the destruction of the source code in promise of eternal happiness, might be a good thing, but this shows that initial set of axioms of the Gödel machine plays a critical role, and they by themselves cannot be formally proven. Why then should we limit its rewrites only to provably beneficial? Maybe hypothesizing usefulness of some rewrites and validating them in practice may allow finding better rewrites for any fixed axiomatic system. I mean, whatever initial set of axioms you built in the Gödel machine, they will be beneficial, even more beneficial, but not provable self-rewrites. And this scientific method of putting hypotheses forward and empirically verifying them may not be formally provable by itself. I mean, one could take the whole history of scientific discoveries and prove within certain soft assumptions, but still there should be such assumptions, that the scientific method will work in the future with certain probability. No one really bothers with this because it would take too much effort. And it's problematic to formally prove that spending resources on formal proof instead of just trying it in practice is provably beneficial. And I said that programmers rarely restrict themselves code with provable properties and spend time on proving these properties, but use empirical testing more often. Even there is a trend towards formal program verification, it is not always worthy. And there is just infinitely many useful programs for each of which you cannot prove each its property. Going back to type theoretic settings for an engine, we can have a minimalistic collection of built-in types and make predictions in vanilla non-incremental universal induction style. But this will render type theory settings not too useful and the system itself not efficient. We don't really propose this. In contrast, we are trying to justify the necessity for emergence of new types at runtime, which allows utilizing the whole power of type system for knowledge representation and reasoning. These types and their constructors should not be considered as the final truth. Rather, they should act as models or theories which have a restricted scope or utility in application to the real world. Maybe this is what P1 implies, but by non-axiomatic systems. But we also don't imply that some metaformalism is needed. It's not the problem of type theory, but a nature of mathematics itself. Also, I didn't talk much about it in my presentation, but I do think that type theories, in particular homotopy type theory, is a viable choice as a basis for developing a cognitive architecture, knowledge representation, and reasoning language. However, it's not all we need. The first thing that we need is support for grounded symbols and first-class citizen. Some grounded symbols, some symbols of type theory itself are grounded. That is, their content is defined externally in some pieces of code. Why this language should not be enriched with more grounded symbols? Then the type of sensory data is not really known and defined within the system. We cannot say that it is, for example, a 2D matrix of real numbers, because it will make any combination of these numbers literally existent for the system, which is just wrong. It's not enough to say that it's just a monad. There will still be I/O involved, and monad is only a wrapper for pure code. Thus, we should rather consider the type of sensory data is grounded in the sense that its constructors are defined in the external world. Basically, grounded means not strictly provable within the system itself. In this sense, if we introduce generalizations and as new symbols as the types or type constructors, instead of inferring everything from the whole interaction history, they should not be too different from basic observations in sense of reference to the external world and incompleteness. Referring to the agent's implementation, for example, to the knowledge base container from the knowledge base itself should inevitably be done through grounded symbols as well. Concluding, although we consider specifically homotopy type theory as a good basis for developing a cognitive architecture language, the cognitive language should have some in addition. In general, these additions can be gathered under the umbrella of grounded symbols. For example, one may want to formalize emergence of new types of symbols using infinity groupoids. And although I am not saying this is not needed, but how a system could invent the possibility by itself or invent something else which was not foreseen but its creators. Also, I didn't describe the concept of grounded symbols in detail in this talk, but I'd like to conclude that the possible answer to this question is to consider them as not an ugly duckling, but as a central element of such system. Thank you for your attention.